Okay, again, couple of announcements for class. Because of a little bit confusion, one student was not able to make it from Changwon, which is very unfortunate. So no class tonight, clear. So I'm gonna give you the 3 makeup class, as I mentioned to you, 3rd week of October, starting 24th Monday, for a week. Myself and my research professor and the 3 students will be out in Florida to present the papers in the conference. So I'm going to do the makeup class spread 1 or 1.5 hour per week for next 3 weeks. So that makes it easier. And 3rd week happened to be the midterm exam week, as I look at the schedule this morning, 8th week. But I'm gonna give you 2 hour. I always give you 2 hour exam. So midterm exam will be like a Monday after we return, which means last week of October. Okay, Monday 2 hour. We can make it during the day, so we might have to give you the 2 hour exam, 2 hour slot, something like a 6 to 8. So I'm very flexible, so think about that. Okay, there will be no complaint because no 2 hour slot. That's what I see it. And this equation is what we really drive the conservation of mass, momentum, and energy. And that's what I just rewrote there. And based on what relations? Hydrodynamic relations. Then today, as I said, I'm going to approximate using acoustic approximation. And I am going to claim that that's equally applicable for the shock problem. Based on what assumption? Hydrodynamics, we developed all this pretty well-known basic, the conservation law. So now I'm going to bring the acoustic approximation, apply to this equation set. Then we can use those equations to do the acoustics work. Then I said I will claim that that equation set is equally applicable to solve the shock problem. How can I say that? How can I say all the acoustics equation I will develop from hydrodynamic relations? I can say, hey, you can use to solve a shock problem. But there is one assumption. Really, you have a nice haircut today? Over the weekend? Yeah. That's good. That's good. Much younger than you are. You know, this is equally applicable for shock problem. The stuff I'm all doing here is not good, is not valid to solve the phenomena right in the vicinity of the charge at the time of explosion. That's the detonation physics. 2 different art. If you want to deal with the phenomena in the vicinity of the charge, or right on the surface of the charge at the time of detonation, that's detonation physics. If you go in the internet, then type in detonation physics or detonation, there are tons of arts, books, papers. But my interest is what happened after about, for the distance of about 10 times the radius of the charge. You follow me? You know, when you place the charge, if the charge is, let's say, 1 meter radius, that's a pretty big charge. 1 meter radius of the charge, then 1 meter times roughly 10, which is 10 meter. So 10 meter away from the charge, all the stuff I'm doing in the class is applicable to solve the problem. Then you could say, why do you do that? If explosion occurs next to the hull, you don't have to solve the problem because it will puncture the hole on the hull. So that's the reason. And Navy's interest is really what's happening. Explosion occurs is a little bit away from the target. Okay, that's the main reason. Yeah, that's the main reason. So here, to do the underwater acoustic wave, the approximation, I'm going to use all the hydrodynamic relations we developed. Few assumptions I'm going to make it, which is a very reasonable assumption. So first assumption, sufficiently small disturbances in a liquid by external sources. That means at the time of explosion, right? Instant time later, there will be no disturbance. I briefly talked about this last Friday. You don't see water is really violently disrupt anything. Everything's quiet. Bang! At that moment, a shock wave will propagate away quickly. And water particles just sit there. Then after shock wave just passing by, then all the water particles just wake up, start to dancing. Okay? So for the acoustic wave, underwater acoustic wave assumption, I can assume such that the sufficiently small disturbances in the water by the explosion, by the underwater explosion, I can recast it like that, okay? Second assumption, density changes. This is water density changes insignificantly compared to its initial value rho naught. What does it mean? The water density is spatially constant. Water density here in the water is about same as water density here in the water or here in the water. Spatially constant. Cast into the equation, that's a del rho over del x. X is a spatial coordinate equal to 0, or del rho over del y equal to 0, del rho over del z equal to 0. The water is, simply speaking, homogeneous water. So I'm not dealing with water density in the Pacific Ocean, well, water density in the polar region, and comparing with Indian Ocean at the summertime. I'm not considering that, because you don't have to consider the such a condition for the naval ship design. You don't need that. In the vicinity means it's really in the same water. But if you feel that's critical, you can assume just like that. Any water, the water is homogeneous for the ship design sense. Okay. And so as I shown in the XY plot here, the rho is really kind of a constant. So showing in the rho versus time t here, rho is really constant. I'm going to call that as a rho naught. That doesn't mean that rho is a constant of time. No. Rho is changing. As a shock wave propagates, it compresses the water. If you cannot compress the water, if water doesn't have the compressibility, then there will be no shock wave, there will be no acoustic wave. It's compressing. The acoustic wave or shock wave is compressive in nature. Okay? So, but if I plot here, so del rho over del t is not equal to 0 because it's compressible in nature. And you will see this the red kind of the oscillations, okay? So against the time t. And rho, you can say that rho is equal to rho naught plus del rho, this is rho, at t is equal to 0, t is equal to 0, any arbitrary time t, okay? So this is really small, this amplitude of this red line oscillation is very small. Then this is equal to rho naught. Nothing to confuse. Remember, del rho over del t is not this is weak. This is not equal to 0. Third assumption. This is really underwater acoustics approximation assumption. Then I can apply this assumption to hydrodynamic relations. Then you can have then beautiful acoustics wave that you can use for shock problem. Okay? So particle, third assumption, fluid particle velocity is always small. Fluid particle velocity is not 1,000 meters per second. Okay? So we are dealing with fluid particle velocity. Okay? Fluid particle velocity. Of course, this is fluid particle velocity. Everything is all calm. So you can say U naught. So this is a shock wave is coming, let's say, from left to right. With, let's say, we always use a C naught. So everything's calm. When the shock wave is passing by, then it does wake up the fluid particle. At the beginning, it was calm. Usually, we set U naught is equal to 0. That's what we usually set. Even if there is a tide or current moving pretty good speed, but which is much lower than the shock wave velocity. Shock wave is about the same as acoustic wave, which is 1500 meter per second. So when shock wave just passing by here, so behind I'm going to call the U. Okay, if I just say that if this is x-axis, okay, this U is caused by the motion of the shock wave, and the range for the ship shock problem, the range of this fluid particle velocity is something like 10 or 20 feet per second. So I can say 10 or 20. I think I mentioned 20 feet per second. Or if you divide by this by 3.2, about the 10 is about 3 point something meter to 8 meter per second. It's not absolute God, you know. I'm in the range, in that range, okay? Because as an engineer, I demand you have some good common sense knowledge. At the field, you don't have any book to look at it. So you can quickly estimate. So how to estimate? For example, we're going to solve that problem, get the solution, P is equal to rho Cu. I give you this already. Before we got this, the solution, if you know the fluid particle velocity, then you know the shock wave pressure. Or if you have a shock wave pressure, you can compute this based on the empirical formula. Then you can compute the corresponding fluid particle velocity. Or the ship is in neutral buoyancy, you can compute the kickoff velocity of the ship. I haven't got there yet. So it has really lots of application as a good approximation. For the underwater explosion problem, for the charge itself, sometimes a 10-pound the charge is same as explosive. 10-pound charge sometimes acting as a 9-pound charge, sometimes acting as 11 pounds of the charge. It has a statistical variation. So it has a statistical variation. So probability density function. So it's supposed to be the exactly this 10 pound. For example, 10 pound has to, that charge has to have the 10 pound, let's say, should have, let's say, 100 psi. Maximum shock wave pressure, let's say. This is a pressure. But when you take a measurement, it's not 10-pound charge doesn't have 100 psi. Sometimes it has that much, well, 110, or here is 90. So it has a variation that you have to remember. There is no such a thing as absolute. So standard deviation is over 10%. Standard deviation, or another way we do is sigma over the mean, which is called the coefficient of variation, or some people call this simply the variability. variability of the charge is like a plus minus 10%, which means it's pretty high. Remember that. It's not only my personal experience, but lots of collection of all the experimental data. It really shows a high variability. In other words, this is like a plus minus could be 10%. If this is a mean value, this is a mean. This could be, in this case, is a minus 10 plus 10 psi. So it's about 10% variations are there. Okay. There's no such a thing. 10 pound will act exactly 10 pound. So we are not living in such a world. We are living with the errors and uncertainty in there. Then to really do the makeup for uncertainty, then you import the safety factor. Safety factor. U is small, and du over the del u over del x, spatial variation of the fluid particle velocity is very small. The fluid particle velocity here, fluid particle velocity here is about the same. So you can assume del u over del x. In this case, this is x direction. That's why we are using u. If it's a y direction, you could use the v. Okay. So del u over del x, or del v over del y, or del w over del z, very small. Spatially kind of independent. Whether the u here along this, the shock wave, behind the shock wave, the fluid particle velocity here, or here, or here, or here, it's all about the same. That's what I'm saying. Okay? So small multiply small, gonna be small multiply small, gonna be smaller. Then you can set equal to 0. So 3 assumption, pretty good, reasonable assumption. Then we learn already the momentum equation. What does it mean, momentum equation? Conservation of momentum. Or it's called Euler equations, or momentum equations, all the same meaning. So this we derive all this relation last week. So capital V is vector notation of fluid particle velocity in x, y, and z direction is minus del p. That's a gradient. So now then this is a total derivative, because V is the function of x, y, z and the time t, right? Then you can cast into the del, partial differential, del v over del t. Then there is a second term. I drove that last week. And this is, I said, set equal to 0 based on what assumption? Based on what assumption? 3 assumption. Third, u multiply del u over del x. So this is what This is a three-dimensional expression. That's only one-dimensional, moving in x direction. So it's a gradient v times v, scalar product, and that's 0. So over here, just to revisit, some students in the past raised the questions. That's the reason I put that in here. So rho could be rho naught plus the fluctuating part, del rho. Okay, over there. Then this guy you split into two. This guy multiply. This is really small, and you can delete that. You can have that term equal to minus gradient p. That equation is very important. Without this equation, without this relation, this is coming down to this equation. This is, I mentioned last Friday, the first order acoustics equation, or shock equation you can say. First order shock equation, this is the first order, but some other people called this is a reduced momentum equation. Full momentum equation is this. This could reduce down to this. Based on this assumption, second term is equal to 0 for the shock problem. Okay. Then if you say, what's the name of this equation? First order, the shock equation, or reduced momentum equation. Remember this. This is very close to this, changing d to partial. Okay? So we're going to bring back continuity equation. What does it mean, continuity equation? Conservation of mass equation. We flash this out here a few times, so it's almost a stick in the brain. So bring back the continuity equation, which is del rho over del t plus divergence is what? Del dot, gradient dot, and rho v. Oh, this tilde is a vector, kind of saying that's a vector. Then divergence is a del dot. I'm giving the same thing over and over again. Make sure it's all gets in your heart. And rho is spatially constant. Then you can really take this guy out here. Okay, if you want to, right? So that's a continuity equation. So you take outside of the divergence notation, which is gradient dot. Okay? So now we know P is a function of rho, one-to-one relation. If you look back, section 2.2, the last page, if you look there, there is a P and rho relation, implicit relation we saw developed there. So del P over del T is equal to dP, because P and rho has only one-to-one. So whether it's a partial or total derivative, the same. dP over d rho, and this S naught is in adiabatic condition, which means there is no heat change in and out. So then I can say del rho over del T. It's a del because it's more than one parameters. So now this is, you can express this C naught as a square root of dp d rho. By the way, I said derive the conservation of energy. Everybody did? And before the end of the class, just to turn in, then I can see it. I want to make sure you all have done that. So this is C naught square del rho over the del T. So here I even draw the line to make the life easier. But again, after you return to your office, sit down and just derive it yourself. Otherwise, everything evaporates. So here is del rho over del T is equal to, from here, between these relationships right there, this is a C naught square. So this is C naught square. And by looking at this guy, then this guy, del P over del T, is a C naught square del rho over del T. So by looking, this is equal to 1 over C naught square times del P over del T. So that comes right from there. This comes right here. Then we're going to bring this del rho over del T here is equal to, move this term to the other side. Then it's minus del naught gradient dot V is what this is. So we use equivalency between this first relation using this is equal to that. And second identity, what I'm using is this is equal to, put this guy the other side, is negative rho naught divergence V or gradient dot V. So you may notice that I'm using the rho naught and C naught. I could use C and rho. The reason I'm using the naught is constant. Rho naught, so use it as a constant. Water density, mass density, use as a constant. Don't worry about the variation, between one point to another. Just use a constant. C naught is the same thing. For design aspect, C naught, 5,000 feet per second. C naught, use as a 1,500 meter per second, vice versa. So then from these two relations, you have right here, this is equal to that, this is equal to that. Then you can take this guy out to get the relations. Okay. So now I'm going to differentiate once with respect to time once again using this relation, this term is equal to that term. Then you can differentiate with respect to time t. Then you have to differentiate right here. If you differentiate delta, this del gradient is a spatial operator, so there is nothing to differentiate with respect to time t, that's a 0. So applies only this. So I'm going to, as you differentiate this part, and that's del p square, del square p over del t square. And that part comes right here, is equal to I put the del naught here. So del, you can take them outside and associate rho naught with the del V over del T. Then I say that here, this is equal to minus 1 over rho naught del P. Where does this come from? That's a reduced momentum equation in just the previous, at the bottom of previous page. So I can replace this guy as what? If you replace this guy for this, rho naught cancels up, minus minus is plus. Then you have a del dot del P. There's a del square P, which is Laplacian P. So Laplacian P, then you have a beautiful wave equation. A lot of time you really start before you solve the problem. Then the first step is to just put down the wave equation. That is called the wave equations. So this is 1 over C naught square del square P over del T square is equal to Laplacian square P. Sometimes I have a bad habit using P as lowercase. Sometimes I use uppercase, but really same thing, okay? The stuff I'm doing. That's really wave equations. Usually you start wave equation to solve the problem, but that's not good idea. But this is all derivable very nicely using conservation law to using the hydrodynamic relations, then apply acoustic approximation, drop the terms, then get down to wave equations. Then it's no longer good for hydrodynamic relations. Okay, so this is wave. Now this equation is really for basic equation for the wave motions. And and Laplacian is a del dot del, gradient dot gradient. So if you look at that, visualize it. Del over del xi plus del over del yj plus del over del zk. That's a del scalar product, same del. Then you will have a del square over del x square plus y term plus z term. Then apply the p to all the terms. That's what the Laplacian term, Laplacian expression for the Cartesian coordinate. But tonight, when you go back, you will, you don't have to drive, takes a little time. You look at handbook. You always have a handbook. You can, or you can look at the internet. Nowadays, everything is all there. And the Laplacian P, you can find expression for cylindrical coordinate and spherical coordinate. You need to do the spherical wave. You need to get the expression for Laplacian for spherical coordinate. We don't handle here for the shock wave cylindrical coordinate. For some situations, we apply some very rare situation. you sometimes use cylindrical coordinate. You know, during the desert storm, the war in 1990, it's not really it's invading forces in Gulf, in the shore, seashore. This is land. One time, one of my students, he graduated a few years ago. He happened to be the Navy commander. He's a lieutenant colonel, but he's called the commander in Navy. He called me from Guam. Then he asked me, they like to make artificial tsunami. Artificial, some example, okay? Use a cylindrical, so-called dead cord. Artificial tsunami, and he said, I am thinking this. Do you, Professor, give us some comment whether it's a good idea or bad idea? So it's a shore. So if I just look at the cross section here, this is a plane view. This is elevation view, and the ocean is here, and this is land here. They put the mines all over the beach. All over the beach they put the mine. Then invading forces cannot go through the minefield. They want to clear the mine. So what they can do is they can drop the dead cord, maybe a couple of dead cord, and put the detonation code like this at the bottom of the ocean, near the shore, near the beach. And they can ignite the one side and the other side, then detonation would occur all the way so fast. It's called a dead cord. It's a detonation cord. Dead cord. O-R-D or C-O-R-D, I don't know. Then that's a cylinder. Just to look at the wave motion for a cylinder type of the explosive, you need to express that equation set in the cylindrical coordinate. Very rare situation. But I told them it's not going to work. It's not going to generate a tsunami. What they are thinking is when explosion occurs in the dead cord, they're going to generate huge plumes, and these plumes can move in that direction, wipe out all these mines. It's a good idea. KAIST students should have some rebel kind of the idea is what we are expecting. Could be in military application, but it's not going to work with many different reasons, so they scrap to do that. So cylindrical coordinate you need in such a situation, but mostly you need Cartesian coordinate to solve the plane wave problem, one-dimensional wave, okay? Plane wave. And another type of the popular wave is spherical wave. Then you need to express in spherical coordinate. For the spherical coordinate, for the Laplacian, you have a couple pages after. I put that in there. Four term, the expression for spherical coordinate. But what I want you to look at is spherical coordinate expression for gradient. Take a look at, okay, you will end up to find that or solve that, whatever. First, the plane wave. Plane wave is one-dimensional wave, and the wave front strength doesn't change. It's the same. Same in the wave front. And that wave 3D, this is a 3D wave equation. Replace this guy here. There is no y term, there is no z term, because the wave is moving one direction, let's say x directions. So then left-hand side, the left-hand side here is, I put on the right-hand side. And this Laplacian, you just keep the first term. Then that's a plane wave, right? So that reduced down, this wave equation reduced down to this equation. Then the pretty well known, the 3D solution, general solution, is called D'Alembert solution. So D'Alembert expressed the solution for this kind of the one-dimensional wave as exactly function of f plus g. What does it mean? What does it mean here? Which is f, this one is a forward traveling wave. From along the x direction, this function is really wave going the positive x direction. And this guy, g, is reflection wave coming back out. When the wave hit the rigid surface, then bang, then has to return. So this part is like a reflection wave. And this part is like an incident shock wave. Incident, whenever I said incidence, is the wave moving to the positive x direction. So that's what the application portion is. And just regular mathematical wording is f is the forward traveling wave, and g is backward traveling wave. Incident shock wave, this is reflection wave in engineering. That's what that is. Then the question is, if you claim that this is in the time domain here, but this is p, solution for p is a function of x and the time t, two variables, and t minus x over c naught, t plus x over c naught. So this is, if you plug this guy in here, then equation is satisfied. So this is the solutions, okay, mathematically, nothing else. And this is in like a time domain. This is a t minus x over c naught. This is like a meter over meter per second. Remaining unit is the second. So this is a time domain function. But you can change it, the expression like this. No problem. This is, but here is time multiplied c naught. Resultant unit is like a meter minus meter. So this expression is really for the distance you travel. We can see better. I feel this is just my way of explaining. You can see better the distance you travel rather than time. So I brought this kind of the way. But if you plug into the one-dimensional plane wave equation, it met. It satisfies the equation. So is good. So by looking at t is equal to 0, initial time, t is equal to 0 is initial position. So if you set the t is equal to 0 here, then this guy is 0, is f, open parenthesis, minus x. This case is g, open parenthesis, the plus x. So I just put down in the coordinate, this is p, okay, because this is p here, and this is a forward traveling wave moving in the positive x, and this guy gonna move in the negative x direction. So look at this, the way I explain. Other people could explain using the time domain, but it's all same thing. To look at the motion of the wave. So in this case, this is what I brought. I can change this t c naught to x. I can put the x here, t multiply c naught here. Same thing, x and the t c naught can just exchange it. Then you just move into the equation, plane wave equation. Then it's happy, it's satisfied. That's a solution, doesn't make any difference. So for explanatory purpose, I can rewrite that as like this. Switch it, who cares? It met the satisfy the plane wave equations. So now let's say this is t is equal to 0. Look at here, t is equal to 0, and this is a waveforms, okay? And if this waveform move the distance after time t naught, if it move, this waveform will move to advance into the x direction for the duration of time t naught. Acoustic speed is c naught. The distance it travel gonna be c naught multiplied by t naught. Okay, then from here, to move back to the original position, you have to subtract. You have to subtract total, this is x, the distance x, subtract c naught times t naught to get to original position, which is left-hand side of this wave train. So you can tell this f is forward traveling wave. The reason I did was some students asked some years ago. So I felt that this is a good idea to explain. For the backward traveling wave, this guy, okay, so in this case, you have to get the, you have to add together x plus c naught times t naught to get back to original position, okay, which is backward. This is moving, this wave train is moving the opposite to positive x-axis. This was here initially, moved on to here, which is a backward traveling wave. Well, anyway, this is kind of the way I explained it. Okay? I think I'll stop right here. We'll continue from page 5 because need a little bit more longer explanations. So it should be crystal clear, because until the end of this month, you have to have a full understanding. Then even without looking, everything you should it should be very clear. That doesn't mean that memorizing. No, don't memorize the equation set. You're not going to get such questions